Hi everyone, in this video here are our objectives. We are going to describe what intermolecular forces are. We are then going to identify the intermolecular forces that govern how hydrogen atoms of one compound interacts with the oxygen, nitrogen, and fluorine of a neighboring compound, and that's going to be followed by describing how these intermolecular forces are responsible for water's high boiling point. So this story begins with identifying and describing something called intermolecular forces. Now let's break down this word, intermolecular. Inter means between. And molecule relates to a substance, such as water. Okay, so between molecules there are forces. There are going to be forces that perhaps hold them together. So that's what we must keep in mind. So if we have one molecule here and another molecule here, will there be a force that holds them together? So now let's identify the intermolecular forces that govern how hydrogen atom of one compound interacts with the oxygen, nitrogen, or fluorine of a neighboring compound. So to best understand this, let's build some molecules that actually have the hydrogens bonded with the oxygen, fluorine, or nitrogen. And to best understand how those molecules might bond with one another, or those elements might bond with one another, hydrogen, when it bonds with fluorine, it takes on a 1-to-1 ratio. When hydrogen bonds with oxygen, we need two hydrogens. And when it bonds with nitrogen, it needs 3 hydrogens. And in this case, it's more commonly written as NH3. Now, let's take a look at these more deeper on the next slide. So let's take a look at hydrogen fluoride first. I want to take a look at the electronegativities. For hydrogen, it's 2.2. For fluorine, it is 4.0. Now let's write these in. And 2.2, 4.0. Now remember, electronegativity is the pull electrons or atoms will have on electrons. And when we see the difference here, it is a 1.8 difference, suggesting that fluorine will pull on those electrons quite a bit stronger than hydrogen will, and that will give it a partial negative charge and hydrogen a partial positive charge. Similarly, let's take a look at H2O. Now, H2O actually looks like this. But let's take a look at those values as we did just before. We have 2.2 versus oxygen's 3.4. And so we'll put in, grab a pen, 2.2, 3.4. And in a similar way, we're going to have an unequal pull on those electrons, giving oxygen a slightly negative charge and hydrogen a slightly positive charge for this one as well. Now, seeing that this molecule is asymmetrical, we also know that the entire molecule is polar. Now let's take a look at NH3. The value for nitrogen is right down here at 3.0. So let me get that out of the way. I'll draw out what this looks like. We have a nitrogen bonded to a hydrogen, and a hydrogen. Our electronegativity differences or values are 2.2 and 3.0. Again, making it, giving it an unequal distribution of charges being shared, and nitrogen ends up being slightly negative, and all the hydrogens are slightly positive. Now we have to keep this in mind when we talk about these intermolecular forces. Now what you see in this picture again is the hydrogen fluoride with the slightly negative charge and the slightly positive charge noted, and I put a circle around it so you would understand that that is one. Now here lies a classic picture. What we have is a picture of how many? 1, 2, 3, 4, 5 water molecules. And note their alignment. And actually, let's look deeper within it to begin with. Notice the oxygen right in the center of that central molecule. And we have a hydrogen and another hydrogen. And note this charge, that slight positive charge for that hydrogen, slight positive charge for that one, and the slight negative charge for the oxygen. But look how it behaves when other water molecules are neighboring it. The hydrogen of one aligns with the oxygen of another. Let me show you. The hydrogen of one aligns with the oxygen of another because of the partial charges. The oxygen of one aligns with the hydrogen of another, and so forth. This is also what's going to be noted with the nitrogens. So I showed you the hydrogen fluoride. This is the water, and I'll draw it out on the next slide. You'll see. Alright, so here I've drawn 3 separate ammonia molecules, these NH3s, with the hydrogen having a partial positive charge. Here's another molecule of ammonia, NH3, with this nitrogen with a partial negative charge. So this hydrogen came close to this nitrogen, and we could say that there is a hydrogen bond between them. And just as there's a hydrogen bond between these two, there would be a hydrogen bond between these two. So that's how it works. Now I don't want to leave you with a false impression that it has to be hydrogen fluorides with hydrogen fluorides with hydrogen fluorides, and it can only be waters with waters with waters. So what I did here is I drew one water next to one ammonia to show that the slightly negative charge on this oxygen could attract the hydrogen of a separate molecule altogether. And I have that depicted here as well, that the oxygen could be attracted to the hydrogen of a different molecule. Now also note how it is I drew the hydrogen bond this time. And this is how you would most commonly see it, with a dashed line. So it kind of looks like a bond, like this bond, but because of the dashed line, it indicates to you that it is not as strong as the other. So now let's use what we've discussed and describe how these intermolecular forces are responsible for water's high boiling point. But to start, we must look a little bit deeper at what boiling point really means. Now, boiling point is when there is enough energy within a substance to overcome its intermolecular forces. So if I were to draw a water here, and another water here, and put in the dashed line to represent the hydrogen bond, the force that is holding this one water molecule to another, we would need to add enough energy to break this bond so that these water molecules can go their separate ways and boil, going from a liquid to a gas. So, in order to boil, we must break intermolecular forces. Now we're looking at water, H2O, oxygen. Let's focus on that for a moment. Oxygen lives right here on the periodic table. Now if you remember, all the groups, or all the elements in the same group, should have similar chemical properties. So that would suggest that if hydrogen was bonded with sulfur, it would behave similarly. If it was bonded with selenium, it would behave similarly, and H2TE would also behave similarly. But when experiments are done, they find that they're quite a bit different. Let's explore a graph for a moment. Now, just as I showed you, we were comparing H2O, H2S, H2SE, and H2TE. And what this chart is trying to tell you is, well, here's temperature on the y-axis, and molecular weight on the x-axis. And, well, as we go from oxygen bonded with hydrogen to sulfur to selenium, the molecular weight is growing larger. And we do see a nice trend going from here to here. But why do we have a break right here? Why is it so different? And the difference lies in the fact that there are hydrogen bonds that are going to be holding together the water molecules. So these hydrogen bonds, although they are considered weak, are strong enough to identify the difference seen here and why it breaks the pattern. And if you recall from previous slides, there's fluorine and nitrogen. And it too helps explain the difference between the hydrogen bonding molecules within their groups. So the reason for the high boiling point for water when compared to the other elements in the same group is because of those intermolecular forces known as hydrogen bonding.